So thanks for clicking this video and watching with me the lecture 3.3 Optical Resonators on our course in laser physics. So what I want to say here is that we will basically just generalize or use the mathematics we just developed in the previous lecture on Fabry-Perot interferometers, but rather than thinking very thin Fabry-Perot structures, for example, acting as an etalon inside a laser resonator, we are rather now shifting our focus to really understand how the actual laser cavity laser resonator works. So we will be really like switching gears rather on a kind of bigger scale resonators that could be of lengths of several centimeters or even meters or so forth, rather than in the previous lecture, we really were considering very thin structures, rather more on the kind of thickness level of millimeters and so forth. But basically the same mathematics works out. So I think there's no really trouble here going with this description. And what we will be doing here is that we will go through a few of the most basic laser resonator configurations and outline what are the free spectral ranges, what are the resonance conditions, and so forth. So basically the kind of main behavior, main characteristics of these resonators, and kind of trying to understand how we can build a cavity in a simple manner. But let's now get started. So I will start first by just outlining the kind of basic motivation for this lecture. So I will be kind of just stating that we want to study next optical resonators, and we want to start with the simplest possible case. So kind of following the Fabry-Perot resonator case we already described the mathematics in the previous lecture. So we consist or kind of assume that we now have a cavity formed using two planar mirrors, and they basically form a Fabry-Perot interferometer. And in between these two mirrors, light bounces multiple times. And as we learned in the previous chapter, in the previous lecture, the specific incident wavelengths propagating light interferes either constructively or destructively, and that's the mechanism that gives rise to these resonances. And if you still remember the transmission function, we do have a transmission function that is periodic. So essentially, this kind of simple Fabry-Perot resonator forms a periodic lines of resonances. So actually, it can be resonant at multiple wavelengths. And these resonances occur physically when the accumulated phase of propagating light during a single round trip corresponds to a multiple of 2 pi. So essentially, we have periodic boundary conditions in our system dictated by the two mirrors. And this is something that we did not really, too much look, or we didn't really look too much into this when we were dealing with the mathematics in the previous case. We were rather more interested in kind of calculating the field distribution of light transmitted through the Fabry-Perot interferometer, but now we are rather more interested in looking how the light behaves inside those highly reflective interfaces or surfaces. And in a more general description, we rather even generalize to a case that we just don't have a single piece of a material, but rather we have two separate mirrors and then some air, some elements, and a gain media between those two mirrors. So that's the case. And now this condition that gives rise to multiple peaks is really that a single round trip phase accumulation corresponds to a multiple of 2 pi within that kind of laser resonator. And that's basically rising from the fact that we have periodic boundary conditions imposed by the two mirrors. And then when we have this kind of a periodic boundary conditions, the total field inside the cavity basically resembles a stationary wave. So we can kind of imagine that we have a rays of light propagating in the forward direction. At the same time, we also have rays of light or fields propagating in the negative direction. And then as an outcome, we have a stationary wave being formed. And this is most of the time the case that we have inside laser resonators. Not always, but most of the time that is the case. So mathematically, the phase condition corresponds to the case that we have the wave vector amplitude k times 2 times the cavity length, and that equals to 2 pi n. And basically that then equals to 2 times nu divided by c, so that's the k written indifferently, equals to L. So this is the phase condition basically that we have. And the resonant frequencies of the cavity are therefore of this form, that the nu frequency equals to n times c divided by 2L. And with the free spectral range, the FSR, the separation between adjacent resonant peaks will be then given by free spectral range equal to c over 2L. So that's basically the kind of like a separation between the peaks. And here, this is a kind of like a multiple integer, so not the refractive index here. So that's the kind of like where do we have the kind of multiple peaks arising. Ring resonators will be the second configuration. So there are also possibilities that the cavity configuration is not really like forming a standing wave, that rather light propagates or doesn't propagate bidirectionally. So it doesn't really form standing waves. And these kind of cavities are called unidirectional. Or sometimes they are called traveling wave cavities, but here a risk resides in misunderstanding, because sometimes traveling wave configurations refer explicitly to some kind of devices where you really don't have a resonator at all. So you might be, for example, a traveling wave amplifier, and then it's not really a resonator system at all. And now we are kind of joining together, coining traveling wave and cavity words, trying to say that we actually have a unidirectional cavity. So please be warned that when you use the word traveling wave, you have to be really careful that your audience does not misunderstand your meaning. Now, ring resonator is an example case of this kind of a cavity. So basically, it's a traveling wave cavity or unidirectional cavity. And now when we go through the phase condition, constructive interference now after one round trip is given by KL times 2 pi n. That's the condition, and this gives us then the resonant frequencies, nu and free spectral range of this form. So basically it's almost like the previous case, but now we are just like losing a factor of 2 in our equations. And sometimes these ring resonators are used to make lasers, but maybe more on that in the discussion exercises of this week. And then final kind of prime example cavity configuration is that we can consider concentric resonators. We could also consider confocal, but maybe we will leave that discussion to the actual discussion exercises. And as we will learn in our next lecture, cavities can also be formed by 2 planar mirrors, let me rephrase. So as we learn during our next lecture, cavities that are formed by using 2 planar mirrors, they are only marginally stable. So this basically means that if you want to make a laser resonator using this kind of Fabry-Perot cavity configuration, it's not a very practical solution, because it's not easy to make a stable cavity out of this kind of cavity configuration. Sometimes having a kind of marginally stable cavity is exactly what we want to have from our cavity configuration, but those kind of cavity configurations are really more related to so-called mode-locked lasers, so ultra-fast lasers. So it's not a kind of like the simple laser physics material anymore, but rather in the next advanced courses we will be dealing with mode-locked lasers. But in certain specific types of mode-locked lasers where we are using Kerr lens mode locking to mode lock the laser, there you actually are tweaking a lot without the stability of the cavity, so that you can make the kind of like mode locking more easy. But maybe more on that later, or maybe during the discussions if you're really interested. But I just wanted to point out that again, as always in life, things are not as simple as they might first seem. So having the most stable cavity configuration is not always what you want to do. But in practice, most of the time it is, and in this course, that's really what we are aiming for. And aiming for kind of illustrating to you the piece of mathematics that can be used to understand how, for example, cavity stability would be calculated. So of course, like here, we do not really need to be dealing with those kind of like complications on the matter. But I just wanted to warn you that there is actually more than meets the eye in this topic. So stable cavities can be formed by not using planar mirrors, but rather by using 1 or 2 curved mirrors. And that's the kind of practical way of realizing laser resonators. So not really using Fabry-Perot cavities, but rather by using more like a kind of curved mirrors or just 1 curved mirror to realize a laser resonator. In general, we can use 2 unidentical spherical mirrors. So in this case, the centers of curvatures could be different. So given by C1 and C2, that would be the most general case. But here we are really mostly interested in the kind of simplest possible configuration. And that's formed when we have 2 identical mirrors. And in this case, the cavity configuration is called concentric resonator. These points, the kind of centers of curvatures, C1 and C2, if they are equal, we can denote them as just C, then lie at the center of the resonator. And this is the kind of simplest possible stable cavity configuration that we can imagine and deal with. And this is what we start with. And this is something that we will be really going through the analysis in the next chapter. Constructive interference after 1 round trip in this case gives us then a mathematics that looks like this. So we have K 2 times L, the cavity length equals of 2 pi n, and L is now 2 times R, and R is the radius of curvature of the mirror. And this gives us resonant frequencies and the free spectral range as given by nu of C divided by 4 times R, the reflection coefficient of the mirrors, and we are assuming that we have identical mirrors times N, and then the free spectral range is given by C divided by 4R. So these are the kind of like equations that give us a behavior of a concentric resonator in the just terms of understanding where do we have the resonance peaks and what is the free spectral range. To conclude now, the resonance frequencies and the free spectral range of all of these different kinds of cavities follow very similar math. That's basically dictated by the cavity length and by the periodic boundary conditions imposed by the mirrors. So basically this reflectivity plays a role here. We do not say anything about the kind of like a practicality and how other factors affect the kind of like cavity configurations and how are they stable, can they be used, how power scaling would like work out with these kind of cavity configurations. But maybe we will focus on those kind of topics more on the discussion exercises where we can really have a dialogue and we can really try to explain to you what are the kind of considerations that in practice dictate what kind of cavity configuration you want to choose. But here, in terms of kind of simple math, when we are forgetting, for example, what higher optical intensities might do for matter, how like intensities going higher might also imply that the system would heat up in a little bit more uncontrolled manner, and that might imply something for the mechanical stability and also for the kind of like a possible destruction of optical materials due to high intensities and heating up in a kind of like a non-balanced way. So we don't really say anything about those kind of topics here, but rather we just want to understand ideally where do the resonances lie and how does the cavity length change the free spectral range. So just the kind of like basic behavior of these kind of laser resonators. And the main difference that we see right now, without going into the practical details of these different kinds of cavity configurations, is that the different cavity lengths affect the free spectral range, and that's the kind of main things that we see here. But please do note that in practice, like a really kind of like why do you choose a given cavity configuration? It's not a trivial matter, and really many things actually affect in your choice. But I think this is something that we should really like progress by having a dialogue. So I won't be saying anything much more on this lecture. So I will thank you for your time, and please join me quickly on the next lecture where we will be really speaking about the stability condition. So we will be like developing the mathematics that we can really calculate how stable a given cavity configuration is. I thank you here, and please enjoy the rest of the day. Bye.